Okay, let's get restarted. Please, Vincent.
Yes. Can you hear me?
Yep, sure.
Okay, great. So, having served you the appetizers to this common...
There is one question in the chatting.
I have a question concerning the really sense general. As far as I understand from the previous section, is a generalization of whenever I kind of it seems that it's kind of mathematical, but I cannot get what it means operationally. Yes, that is the perfect question. Perfect question. Because that allows us to segue to the next section on infinity order running common information, where we will indeed have an operational sense of the notion of really common information, at least for the order infinity. Okay. Now, intermediate orders may not be of great interest apart from establishing mathematical techniques for us to tackle the most important orders, which is 1 and infinity. Because there is really going to be an operational meaning to the infinity order really common information, as we will see from this part of the talk. So I just wanted to say, but before someone interjected, which is very, very fine, because the more questions you ask, the more lively this becomes. I just wanted to say that I've already served you the appetizers of the course, the meal, and now I will serve you the main course. All right, the most exciting part. The dessert is also going to be very exciting. All right. So Haiwan, when is the next? When is the second segment going to stop?
So 3:20, please.
Okay, no problem. A lot of time. So maybe you can tell some jokes along the way. All right. So now we're going to talk about exact common information. Remember that in the distributed source simulation scenario a la Wiener, we mandated that the normalized relative entropy goes to 0. Normalized relative entropy. Okay. So this is the normalized version. And we also saw some variations just now where we mandated that the really common information of order 1 plus s goes to 0. What if instead we require this very strong, seemingly very strong condition to hold? That is, for some special n, these two distributions are exactly the same. Okay? Very special n. So if we use this thing known as fixed length block codes, that means the block length is not moving. It's not a random variable. Okay? Then we need the rate up to this, which can be as large as the minimum of cardinality of x, cardinality of y. So that is basically a vacuous result. Vacuous, not meaningful. So if we restrict ourselves to fixed length block codes, that means we are using block by block. That means that this guy here must be at most 2 to the nr. Okay, that meaning fixed length block codes. Then we cannot do better. We can only do this trivial thing. It's just like if you demand that you in the source coding problem, okay, in the source coding problem, you have this compressor and you have this decompressor. You want xn to be equal to x hat n exactly. Then how much rate do you need? You need rate up to log cardinality of x, right? So that's very large. It's vacuous. All right, if you want these two to be exactly equal. So that's vacuous. So we need to somehow change this notion of fixed length block codes. So in come Kumar, Lee, and L. Gamal, who introduced the notion of exact common information in this paper that is only present in conference version form, because there's one thing they couldn't solve. Okay. And so we are going to solve it now. Okay. So I'm going to introduce now the exact common information framework. If you look at this picture here, you'll see that the framework seems very, very similar to that for the fixed length case, for a Wiener's common information case. So we have a synthesis code. We define a synthesis code as a triple of objects, where we have two, what are these called? Stochastic encoders, just like before. But now we have this thing called, let's call it a, what do you like to call it? Let's call it a common random variable if you wish. Okay, common random variable. Now, this common random variable is any, not necessarily uniform random variable, but it is discrete. So its alphabet can be a subset of natural numbers. Okay, so the distribution induced by this code is nothing but the average of the synthesized parts, synthesized x and y, average over, so this is the synthesized x and y n, all right, is averaged over the common random variable W. So that's the averaging distribution. So recall that in the Wiener problem, this guy here is nothing but 1 divided by 2 to the NR. Okay, or 1 divided, if more precisely, 1 divided by the message set. Okay, but now we allow this general distribution here. What do we then mandate? We mandate, in fact, exact common information, that this reconstruction is exact for some n, some large enough n. Okay, now how do we measure the performance of this code? Because the notion of performance is gone. Since, okay, if there is such a code, then it's good, right? So what's stopping us? All right, we want the rate to be as small as possible, but how do we define rate in this case? How do we define rate? Now we define rate through the notion of the entropy of the common random variable. Not we, but Kumar Lee and Elgamal. Now, if you recall chapter 4 of Covert and Thomas, we can compress WN using a prefix-free zero-error variable length code. Such a code exists. You can construct a Shannon-Fano-Elias code or a Huffman code. All right, that is nothing but something that brings you from the message, brings you from the alphabet of W to the set of all finite length bit strings. Okay, and the length of W is basically L of W. Okay, so for example, if you go to 0, 0, if the symbol A goes to 0, 0, then the length of A is equal to 2. All right, you know, recall these sort of things. Right, so you can use a Shannon-Fano code or Huffman code, no matter what you use. By Shannon's zero-error compression theorem, the average length is sandwiched between this and that. Okay, this is because of some integer constraints. Okay, this is a strict inequality and this is non-strict. This makes a difference. It doesn't make a difference in our discussion, but it makes a difference whether you're correct or wrong in an exam. Okay, which implies that these two limits are the same. Okay, so instead of the asymptotic rate of the code, I can basically use a surrogate, which is the normalized length, normalized average length of the common random variable. Okay, so it makes sense to now define the exact common information to be the minimum rate for which there exists some n such that we attain perfect reconstruction. Okay, so you know from information theory that if you use a Huffman code, all right, in the standard source coding problem, you can get down to the entropy. If you consider fixed length block codes, chapter 3 of Covert and Thomas, okay, then what you can do is we can use the AEP to get to the entropy. So in the lossless source coding scenario, either almost lossless or lossless, the fundamental limits are the same, entropy, all right? That's what I teach. Then, okay, how about in this case? Well, it is not too difficult to show, and this is our book, all right, that the exact common information as defined in this way, note that there are two differences vis-a-vis the Wiener's common information. One, we need exact, but second, we are able to use variable length codes here. Okay, there are two differences, variable length and exact versus fixed length and approximate. Okay, but nevertheless, you can show that the exact common information admits this multi-letter form. Multi-letter form. Okay, so this is a multi-letter characterization. This is a half a page proof, right? Now it is very easy to see from this, okay, because essentially this is bigger than I of Wn, x, and yn. Okay, and then you can single letterize this, right, using standard techniques. That the exact case is bigger than the Wiener's case. It's not smaller, all right, to be precise. It's at least as large. Then the question is, an open problem posed by Kumar Lee and Elgamal is whether there exists sources such that the exact is strictly larger than Wiener. Okay, so this was a problem posed in Kumar Lee and Elgamal's original paper, and in fact, it's shown here. Let me read this to you because it's very nice to read. All right. As expected, the exact common information is greater than or equal to Wiener's common information. We have this. This is their notation. All right. In the following section, we show that they are equal for the SBAS example. I'm going to show you this as well. Okay. I'm going to explain to you why they are equal. We do not know if this is the case in general, however. Okay. So in it, another part of their paper is the following. This is the conclusion. While this multi-letter characterization is greater than Wiener's common, is in general greater than or equal to Wiener's common information, the main open question is whether the exact common information has a single letter expression? And is it always equal to minus common information? Is there an example of a 2 DMS, 2 discrete memoryless source, for which the exact common information is strictly larger than minus common information? So that was left as an open question there, and we are going to attempt to answer it. Okay, so this is the motivation. All right. Now we establish this. Conjecture. We basically resolve this conjecture by means of a couple of steps argument. The first step is this equivalence theorem that we showed. Equivalent. We call this equivalence theorem. Okay, so we show that for any source on a finite alphabet x, y, all right, we have that the exact common information is equal to the anomalized infinity Rönnie common information. So this is the exact, we establish that it's the same as the anomalized infinity order Rönnie common information. Okay, so no matter what source you give me, these two are the same. So what is this? The first step. What is the second step? The perspicacious student in you would know that we already have bounds on this guy here. We have single letter bounds. Just now I showed right before the break. So if we are able to evaluate those bounds in a very tight manner, then we immediately can evaluate this guy. So that's the strategy. Okay. So this is the picture. If you only take home one picture, take home this picture. Now this is the order, the Rönnie order. Okay, from 0 to infinity. So right here, as I mentioned, less than 1. Very boring, because this is nothing but Wiener's common information. Okay, and this is Wiener here. Flat here. Now from here to there, it's more exciting. Why? Because we grow. Rönnie common information grows in general. Okay, we do not know that it grows before our work, but it grows. And at the very end, at infinity, you recover exact. I want to remind everyone here that these things have meanings. All right, this is basically fixed length and infinity Rönnie approximate. This right here is, however, variable length and exact. All right, so you see that this is better than this. So this is better than this, but this is better than this. So it's not clear. It's not clear which one is, which one dominates. But then these two effects somehow cancel out, such that these two become equal. Okay, so that's the beauty of this theorem, which we call the equivalence theorem. Okay, so I want to show you some elements of this proof. You don't have to remember everything. You just have to remember maybe the big idea. All right. So how do we show this? Whenever we have an equality, we have to show this way and we have to show this way. There's only one way of doing it, right? So what we are going to show first is that if you give me a rate R, Rönnie common information code, I can produce a rate R exact common information code for you. Okay, this is one direction. And this leverages ideas from the original Kumar paper and Villambi and Cleaver. All right. So what does it mean for you to give me a rate R infinity order code? That means that there exists a rate R Rönnie common information code such that the infinity order common information can be made as small as you like. Let's fix an epsilon. Say epsilon 10 to the minus 6. Okay, very small. Then you can rearrange this. Okay, this one is what? This is log of t x n y n over pi x n y, like this. So this is less than epsilon. So basically you can recover this from here. Okay, that's the meaning of infinity order. All right. So now once you have the blue relation here, all right, you have the blue relation here, then you can create this distribution. Now this is a bona fide proper distribution. Why? Because it is non-negative. Since 2 to the epsilon this guy minus this guy is greater than 0. Okay, this is the proper distribution. It doesn't have any negative things. And this adds up to 1. All right, so you need to check that. And that's why the infinity order is useful. All right, and hence, by massaging this, by rearranging this, you can write pi, the target, as a mixture distribution. So these two coefficients add up to 1, a convex combination if you wish. Okay, so this is the synthesize, and this is the target. And this is basically algebra. All right, algebra distribution. Now, what do we do? What do we do here? Okay, don't read all the words. Listen to me. You take a coin. All right, this is a coin. The coin has this is the head. All right, the head probability head is equal to 2 to the minus epsilon. All right, probability tail is 1 minus 2 to the minus epsilon. You take this coin, you flip it. Okay, you flip it. If it turns out heads, this guy here, then what happens is you then use the Renyi common information code, the infinity order Renyi common information code that was given to you. If it turns out tails, bottom here, with this small probability, then you will use full rate, as much rate as possible, full rate. Everything is completely lossless. But this happens very rarely. This happens most of the time, common. Okay? So what happens here is that by definition, okay, by definition of this randomized time sharing scheme, if you wish, you can generate the exact target distribution, okay, just by this formula here. Okay, and what is the total rate? By the law of total probability, this simple probability thing. Now, you need this preamble here to encode the bit, the coin. The coin gives you this thing, 1 over n. All right, what does this come? When the coin becomes heads, you have this probability, but the rate is r. When the coin is tail, you have this probability, and you have this full rate, very heavy rate. But never mind, when n tends to infinity, this goes, all right? And you take epsilon go down to 0, then you get r. Beautiful, right? You have created a exact common information code that generates this exactly and has rate almost r plus epsilon, all right? So this is one part of the whole argument. Basically, you toss a coin, all right? Now, in the other direction, okay, if you give me a rate r exact common information code, all right, I need to produce to you a rate r infinity common information code to establish that t exact is equal to t infinity unnormalized. Okay, so this idea here is basically multi-letter coding, all right, in information theory parlance. So you take a very big code, all right, basically you have this long block length here, all right, you take into blocks of size k, and you take many k's, right, and then you will see what happens. You let k go to infinity, you let the number of blocks go to infinity here. Now, people who do information theory use this all the time, all right? When do people use this? When do people use this? What is it called? Markov method or something like that in relay channels, right? So anyway, let's create a rate r exact common information code. This is a sequence of them that is indexed by k, all right, as I mentioned, such that you have the desired rate. So this is the code that you're given. Okay, you can then create this. So, however, this WK is not uniform. All right, as I mentioned, exact common information code, the W may not be uniform, but we need to produce a Wiener type code such that M is uniform. Right? We need to produce this code that M is uniform. So what we're going to do is to simulate W using 2 Renyi source resolvability codes. Now, so we are going to have this uniform random variable, and we are going to create these 2 blocks to create this not uniform W. Okay, for this we need some distribution shaping technique, which is called source resolvability. And I'm going to illustrate it here. So this is the set of all possible sequences of WK and, all right, K indexes the sub block length, N indexes the big block length, if you wish. All right, and then there's some typical set here. All right, so now you take a M that is uniform on this set, okay, and for every element here, you're going to throw it uniformly at random into one of the elements in a typical set here. All right, like random binning, if you wish. Now, when will we succeed? Okay, if this is big enough, this KR, the effective rate here is KR. If KR is big enough, we will succeed in covering this part here, right? We will succeed in the sense of driving the infinity Renyi common information to 0. And this was done in one of our previous works. If the rate is large enough, basically if the rate K entropy, Kr is bigger than the entropy of P of Wk, we will be okay. All right, this is just standard resolvability, okay, for the source part, not the channel part. So we have this picture here, and what have we? We are given this channel or stochastic kernel, and when we pass P of Wn, product distribution, into this channel, we get the target distribution. If we pass this, all right, which is the shaped distribution here, into the channel, we get the synthesized distribution. But what happens here is that the Rönne divergence, no matter what Rönne divergence you use, you have a data processing inequality, which means that the Rönne divergence of these guys here, the Rönne divergence of these people here, they are going to be less than the Rönne divergence of these people here. Okay, there's a typo here, this should be K. Right, the Rönne divergence here is less than that of the Rönne divergence there. So this guy here goes to 0 by source resolvability. So by the squeeze lemma, this guy also goes to 0. So this completes the proof of the equivalence theorem. Of course, I have left out a lot of lemmas. But after establishing this equivalence theorem, which is here, in the middle, in the past, for the Rönne part, we had bounds on the we had bounds on the infinity order Rönne common information. Okay, this guy here had bounds the upper pseudo and the lower pseudo common information. Okay, so we have gone, what have we done? We have gone from a multi-letter expression given by Kumar, okay, which is this, to single letter bounds. We have not completed the story. We don't have a single letter expression, but we have single letter bounds. Then the question is, presumably, the bounds are more amenable to numerical evaluation. And hence, can we do better than this and evaluate this bound and this bound, for example, for the DSBS, and say something meaningful? Okay, because single letter things can be controlled, multi-letter things cannot. All right, so let's go to the DSBS. This is the discrete, doubly symmetric binary source, which admits this Wiener interpretation where A convolve A is equal to P. This is 2A 1 minus A equals to P. All right, this is the DSBS. We are coming to the climax. All right, so for the DSBS with crossover probability P between 0 and half, not including 0, not including half, we can evaluate the common information, exact common information exactly, because the upper and lower bounds match. Now, we are not very smart in doing this. Because the auxiliary random variable here, we use Wiener's. And for the lower bound, we also use Wiener's converse technique. But because our bounds are single letter, all right, just like Wiener's common information, the evaluation becomes amenable and we have this closed form expression. The details are not important. The important thing is that you look at this, and if I give you MATLAB, you can plot this, probably in less than 1 minute, which is exactly what I did in the next page here, where we plotted the exact common information for P running from 0 to half, and Wiener's common information here for the same range. And what do you see? They are different, all right? And we can actually calculate the difference exactly. There's an analytical expression for the difference. So there's a gap. So for the lossless source coding scenario, like in chapter 3 and 4 and Cover and Thomas, variable length, fixed length, all give you entropy, right? But in this problem here, Wiener versus exact common information, they give you different answers. They give you different answers for the doubly symmetric binary source. And here we answer the open question in Kumali and El Gamal, that there is this gap here. And this gap is not because our MATLAB is bad, all right, or our computers do not have precision. This gap is a real gap, okay? So this answers the first open problem in this tutorial. We will come up with 2 more later on. So I want to give you intuition as to why exact is bigger than Wiener, okay? The next few pictures that I draw are going to be very cartoonish, like cartoon, you know, like a Peppa Pig cartoon. Now my kids like Peppa Pig, so I talk about Peppa Pig cartoon. I even use the Peppa Pig colors, all right? So here we have the typical sets, right? This is the strongly typical set on the X side, this is the typical set on the Y side. And what is this thing that I color here? This is the jointly typical set, if you wish. Okay. So note that the product of the typical sets, marginal typical sets, is not the jointly typical set. The jointly typical set is smaller in general. Okay. So we are listening. So Wiener's common information, what does it require? It requires us to drive the relative entropy between the synthesized and the target to 0. It requires us this. But what is this guy here? This involves a log of p hat over pi, right? So as long as this guy here goes towards 1, we are happy, right? Because then the log here becomes 0, all right? So we require this guy to go towards 1, which means that this ratio here should be 1 plus little o1. Little o1 means very small, okay? But for what? X and Y. For X and Y, only in the typical set, okay? Only in the typical set. So the picture here is as follows. We just need to cover this part here, all right? You need to cover this main part. But what about exact common information? The picture for exact common information is this picture. Why are there so many squares? All right, blue squares. Now, exact common information requires us to drive the infinity order to 0. What is the meaning of this? This means that we require log of p hat pi to go to 0, which means that this must go to 1. Okay? But this is not completely true because I've missed out on the support here. It makes a difference. The support of over p hat. All right, there's a support that is important here. All right, so really common information or exact common information, I think I'm not making this very clear. So the infinity order between p and pi, all right, this is equal to the max over xn yn in the support of p hat is p hat xn yn log of p hat xn yn over pi xn yn. So this needs to be taken into account. This is this. Okay, and we drive this to 0, we need to drive this towards 1. Okay, and this is exactly what's written here for all x and y and the support. All right. So, but what is the meaning of the support? The support is actually now by the definition of infinity order common information, and particularly this Markov chain here. All right, we have that the support can be decomposed into these. But what is this? This is the Cartesian product, a union over a bunch of Cartesian products. Cartesian product. Okay, each one for a fixed W, we have one square here, another W with another square here, another W with another square, and we have many squares here. There's a Cartesian product, they look like squares. So we have a bunch of squares here. This one is maybe one of these guys here, as you can see. This one of these guys characterizes this square here. But as you can see here, you have many such squares, but then some squares have overflow here. So we call this the type overflow phenomenon. The type overflow phenomenon, right? You see here. So you need more space for the exact or infinity order any case. You need more space here. Okay. So when is exact common information exactly equal to Wiener's common information? When the geometry of the problem is so beautiful, such that there is no overflow here. There's no overflow in the geometry. Okay. So when is this the case? Well, a sufficient condition was derived by Villambi and Cleaver, which says that if you fix W, every W, you know either Y or X. So if the product of two numbers, say A, B is equal to 0, either A is equal to 0 or B is equal to 0, right? Yeah, right, this must be true. So either this is equal to 0 or this is equal to 0. So that's a sufficient condition by Villambi and Cleaver. This means that the coupling set between these two conditional distributions is a singleton, which means that the typical set of the joint distribution is almost the same as the union of the product of the marginals of these conditional typical sets. Okay, which means that the support is almost the same as the condition of the jointly typical set, and there is no more type overflow here. So this condition here gives rise to all these. And so we are able to say no type overflow, then they are equal. Okay. So when are they equal? Do we have an example? Let's look at an example for sufficient condition that was studied by Kumali and El Gamal 2014. Okay, they studied the SBES. What is the SBES? Well, you have this symmetric thing in the input. half, all right? Then you pass it through a binary erasure channel. You know, in information theory, we are only interested in two things: binary symmetric channel and binary erasure channel. Everything else is too complicated, right? So binary erasure channel, let's look at this. Now, the Wiener representation of this, the Wiener auxiliary random variable for this SBES, symmetric binary erasure source, is given by this. Now, this is not our work. This is due to Cuff, 2012. All right. So he said that, okay, the Wiener auxiliary is basically BEC P1, BEC P2. Okay, you split this BEC into two parts. It seems obvious, but this requires a proof. And the parameters cannot be arbitrary. You need to satisfy this condition in order for these two distributions to be the same. Okay, so why is this now having an exact common information the same as Wiener? If you look at W here, right, and if you know that W is equal to 0, then X must be equal to 0. There's no uncertainty, because if W is equal to 0, then it can only come from here. In a completely symmetric way, if you know that W is equal to 1, it can only come from here. You know why exactly, all right? The only leftover choice is W is equal to E, in which case you know that Y must be equal to E. So if you know that W is equal to any little w, you either know what X exactly is or what Y exactly is. Does that make sense? So in that case here, you see that we can actually provide a different explanation for why Wiener's common information is the same as exact common information for the symmetric binary erasure source, which is this. Okay, this is due to Cuff. All these equalities are due to us. Okay, so this is actually a story for exact common information, the story. All right, so now I want to talk about something that is an extension of the story for exact common information, which we call approximate and exact channel synthesis. Okay, now I think I want to go a little bit faster here, all right, because this is a small little generalization of the previous theory. Okay, I want to spend some time on matrix factorization. Okay, so I just want you to look at the picture. So we are given a joint distribution, and what is the channel synthesis problem? This is the Cuff problem, all right? Right, so you are given a shared key here of rate R0, okay, and this W has rate R. So now there are two rates, R and R0. This is called the common randomness rate, and this is, I don't know what it's called, but let's call it communication rate, okay, because there's some communication here. Okay, so this is the setup, and what do we desire? What is a desideratum? We want to ensure that the synthesized distribution is either approximately the same as the target distribution or exactly the same for some n. Okay, this is for a large enough n, as n goes to infinity. Okay, so equivalently, because we don't really care about the input source, all right, we just care that this and this, the channels are exactly or approximately the same. So this is called the channel synthesis problem, all right? So we can consider approximate channel synthesis under any criterion that we like. For example, the total variation criterion. And now we have to consider the region of all achievable rate pairs R0, R, and we can denote this by R Wiener. Okay. Now notice that if I have no common rate R0, if I have no common rate, this problem reduces exactly to approximate distributed source simulation that looks like this in the past. Okay, so M here, and we want to generate Yn, Xn here. Okay, it looks exactly the same. There's this common link here, and you're generating this. It doesn't matter where the directions go. Okay, so the minimum compression rate when we have no shared randomness is exactly Wiener's common information. Now, however, when R is equal to infinity, when R0 is equal to infinity, you have infinite amount of common randomness here. Then it's easy to show that the amount of the minimum communication rate is the mutual information. Okay. So it was shown by Cuff, okay, that this trade-off is completely characterized by this region here. And this region is sketched here. So if R0 is equal to 0, okay, we are looking here, then this rate is the Wiener's common information. All right. If R0 is in fact infinity, very large, then this turns out to be the mutual information. So by varying R0 in this range here, we actually get a continuum of common information measures here. All right, and this is the entire rate region. Okay, so that's the classical theory. That is a generalization of Wiener to the case where we have some shared randomness between the terminals. Okay, how about exact channel synthesis? In exact channel synthesis, just like before, we demand that this joint distribution is the same as the synthesized, is the same as the target for some large enough n. And just like exact common information, we allow for variable length codes. If we don't arrive for variable length codes, all bets are off and we cannot do anything. All right. Now, if R0 is equal to infinity, now Bennett and his co-authors showed that the minimum rate is the mutual information. And this is completely analogous to this point here of approximate, completely analogous. Okay. Now, the best trade-off between R and R0 for the exact case was studied by us maybe 2-3 years ago. Okay. And we can see, just for the doubly symmetric binary source, that if we restrict ourselves to R0 equals to 0, that means this is the exact common information problem. It lies here. It lies here. Then we see that we will get, what do we get here? We get Wiener's common information here, and we get exact common information here, and there's a gap. All right, there's a gap for the doubly symmetric binary source. But we have fully also characterized, this whole trade-off in full, all right, by using similar techniques. So the region of rates for the exact case, the region for exact is a strict subset of the region for Wiener, or the approximate case is approximate. So this is completely analogous to the exact common information problem, except that we have this additional rate here. Okay, so this is a strict subset. All right, so it seems like now I've only talked about information theory, right? What about satisfying the people in the audience that don't care about information theory, right? I want to talk about linear algebra now. So what is linear algebra? What is this linear algebra problem? And how is it connected to information theory? Let us talk about it. Let us consider the non-negative matrix factorization problem. What is it? Well, you are given a matrix M. This matrix M is a very large matrix. You wish to find a low rank decomposition, all right? Either approximate or exact. So let me draw a picture. What's the point of this whole exercise? You have a very big matrix here, all right? And you want to decompose it into two smaller matrices. All of them are non-negative, so all the elements here are non-negative. All right. You want to decompose them into two non-negative matrices such that the approximation here, such that what you get, this is equal to UV, all right? Such that this guy here is either approximately the same as M or exactly the same, okay? So we are only interested in exact factorization. So this topic here is a very rich topic, and I cannot possibly do justice to it in the time that I have. I may be giving another tutorial on NMF some other time, maybe next year's ICAS. So if you're interested, I can talk to you about NMF. It's also another of my tech topics. We're only interested in exact factorization at this point. So the pertinent question is, if you give me a non-negative matrix M, how much R do I need in order to find an exact factorization? So what is the minimum R so that there exists U and V such that U and V exactly equal to M? So this is the non-negative rank problem. And how is this connected to information theory? So let me define the notion of the non-negative rank properly. Given a matrix M, non-negative matrix, okay? The non-negative rank denoted by rank plus M is the smallest integer R such that you can write M as UV, basically UV, like follows. So the picture is as follows. You have this big matrix here. You want to find the smallest. Okay, sorry. You want to find the smallest R here, such that you can get the resultant matrix here. This is the M This is m hat. You want this to be equal to m. This is u, this is v. And you want the smallest r here. Obviously, the bigger the r I give you, the easier this task is, right? You need to constrain everything here to be non-negative, all right? So one simple observation is that the linear rank is the usual linear rank. The linear rank is not greater than the non-negative rank, okay? Why? Because the linear rank, you're allowing these factors here to be anything, any vectors, okay? Any vectors, not necessarily non-negative. So there are fewer constraints and you can drive this to be smaller. Now, then can this gap here, okay, this gap is generally a gap, it's easy to construct. Can this gap here be arbitrarily large? Can it be very, very large? That's not so difficult to construct. So for example, here, let's consider this matrix. You have m numbers, m real numbers, and you've considered the so-called distance matrix. So the distance matrix is such that every ij, mij, is basically equal to ai minus aj squared. Okay, so that's the distance matrix. Okay, so this distance matrix has zeros along the diagonals, and along the off diagonals you have the squares of these numbers. Now, what is the linear rank here? By a little bit of algebra, you can reduce the matrix into this 3-column multiplied by 3-row factor. So the linear rank is not more than 3. Now it is 3 if there are at least 3 distinct numbers here. And if there are at least 3 distinct numbers, then these guys here are linearly independent, right? Then you have rank exactly equal to 3. But if we look at the original problem here, okay, the non-negative rank, however, is very large. It's at least constant log m. So as I let m go to infinity, this rank and this non-negative rank and this user rank can be very big, arbitrarily large. Okay. So can we talk about Wiener's common information for non-negative matrices? So let m be a non-negative matrix. Now, because it's non-negative, if we just normalize by the sum, so this guy here is basically the sum of m of xy, then we get a probability distribution, right? We get a joint probability distribution, which we can call the target distribution pi xy. Okay. Now we can create a vector with a random variable w. We say that a random variable w is a seed or a common random variable for pi xy if it satisfies this Markov chain. All right. So pi xy is essentially equivalent to m, the non-negative matrix, if I get rid of the scale. Okay. Then any seed gives rise to a non-negative matrix factorization. Okay. How to find this non-negative matrix factorization is in some other tutorial. Okay. So we can then define, this is a definition of this guy here, define the notion of Wiener's common information for a non-negative matrix as the Wiener's common information for the distribution that is induced from this non-negative matrix. This makes sense because this guy here is non-negative everywhere and it sums to 1. That's required by a distribution, right? So it makes sense. We can then make this definition. Okay, so once we make this definition, we can then relate Wiener's common information to the logarithm of the non-negative rank. Okay, this is a connection. All right. So the proof is straightforward. Let M have an optimal NMF. The optimal NMF means there is as few elements as possible, as few W as possible. So we attain the non-negative rank, and we define the seed in the following way. Now, by flipping this around, by using Bayes' rule, we can get P of xy given W from this. All right. And what you notice here is that, this is now independent, right here. So x, w, y forms a Markov chain, and we have this sequence of inequalities here. Okay, this guy here is the minimum of the mutual information, which is upper bounded obviously by the mutual information. Mutual information is obviously upper bounded by entropy. Entropy is obviously upper bounded by the logarithm of the cardinality. But because I chose an optimal NMF, this is true. The cardinality is as small as possible. So this proves this theorem. Okay. So you may wonder, every time we prove an inequality, we need to wonder whether this is tight, whether this can be equal, or whether this is arbitrarily loose. So these two are very big. The gap is huge. And indeed, the gap is huge. Let's consider the diagonal matrix given by the following. Now, the rank is M. The non-negative rank is M. Okay, what is Wiener's common information? So the Wiener's common information is upper bounded by the entropy. But because X is equal to Y deterministically here, so you can drop one of them and you can talk about just the entropy of X. Well, you know what is the distribution of X is basically given by the following. So this is 2, 4, 8, and 2 to the M, diagonal matrix. So you can substitute this inside here. Okay, suitably normalized by sum 2 to the J up to M. Okay, but this has a closed form expression, and in fact, it's always less than or equal to 2. All right, so this guy here and this guy here can be arbitrarily far apart if I increase M. Okay, so it seems like this relationship is not fundamental. It's just some random bound. All right, not fundamental. It seems. However, the final theorem that I'm going to present in this part is as follows. Okay, answers this question. Is there a fundamental relationship between Wiener's common information and the non-negative rank or its logarithm? Okay, is it fundamental? And indeed, about 4 years ago, this was shown to be fundamental, but we can interpret this using information theory. Okay, so you give me a matrix M, all right, that is suitably normalized. So it's a distribution. All right. Now, if you allow some slack parameters, take n sufficiently large. All right. Then you can find a matrix M that is parameterized by the slack parameters, epsilon and delta, and the block length, if you wish, n, such that this is the n-fold Kronecker product of the matrix M that you started off that you're given. You can find a matrix in the delta neighborhood such that you can find a sequence of matrices such that the normalized logarithm of the positive or the non-negative rank is equal to Wiener's common information. So this is a theorem shown by Braun and his co-authors. But, you know, as information theorists, we find this very strange. How come this thing to do with numerical linear algebra, this is linear algebra, how come this gets connected to information theoretic quantities? Is this very natural? In fact, this is completely natural. If you have listened to my talk, completely natural. And you can reconstruct this result on your own. Why? Okay, why? Before I say why, the punchline, the moral of the story is that the normalized logarithm of the non-negative rank of an L1 perturbed version of the Kronecker product here is equal to the Wiener's common information. Okay, but we could have reconstructed this on our own. Okay, why? Well, this basically just says that Wiener's common information is nothing but TV's common information, total variation common information. Here, Wiener requires normalized divergence to go to 0. Here, you require the p hat minus pi, basically the synthesized and the target distribution goes to 0. These two are the same thing. Why is that so? Now you notice that this part here looks like this, the total variation. Okay, if you make the total variation small enough, that is what this is saying. Okay, this part. Next, why this is Wiener's common information. Okay, so we make the total variation small enough, we can get to the Wiener's common information. So this is basically saying, this is just another restatement of the fact that we have already learned, that total variation common information is the same as Wiener's common information. And in fact, we have proved much more. We have proved a strong converse as well. So we have come full circle here. Come full circle. All right, we talked about total variation common information. We talk about Rényi common information, exact common information, and we go back to Wiener's common information from a completely different perspective from the viewpoint of numerical linear algebra. Okay, so we connected information theory to some aspects of numerical linear algebra, but this is completely expected to us because we already know that total variation common information is the same as Wiener. So, Haiwan, you said 220, right? And
yes.
Now it's exactly 220. So
Right, perfect timing. Maybe a student or attendee can provide any questions to Vincent through the Zoom chat during the break time. So we will have 10-minute break. And before we actually move on to the next context, maybe I can ask just one more question to you.
Sure.
Yeah, about the second session. So I just wonder about the definition of the exact common information, since you motivated the exact common information from the finite length version, right, to have the exact reconstruction of the given target distribution.
Yes.
But the rate you actually look at is the asymptotic rate.
Yes, that's right.
Right. So
everything can be. Sorry. Go ahead.
Oh yeah, of course I can say that in the definition you look at the asymptotic rate and then consider that condition, the exact equality condition for some n. But if we actually start from the motivating problem that for a given n we want to achieve that exact reconstruction, how that kind of question can be related to the definition of the exact common information.
Yeah, this is very sharp. But if you notice that I started off, there's no typo here. All right. We require, in fact, that this holds true only for some n. Okay. It's not that, you give me an n, I need to produce a code that has this property. All right. So I only guarantee you that I can produce this property for some large enough n. One n is good enough. So it then makes sense to talk about this limiting procedure, because as long as I hit one n, I hit one n such that I have this desired property is good enough. For some, this is important. It's not for all. Yeah.
And of course, the integer multiplication of such given n will also have that exact.
Yes. So suppose you have this special n, say n tilde, that this is satisfied. Of course, you will satisfy 2n tilde, 3n tilde, and so on. So you have an infinite number of such n's that work.
Yeah. I see. Okay, thank you.